Yeah, hi guys. So today we are going to present a presentation on war stories with Kubernetes. Before that, like let me introduce myself. My name is Vitesh Sharma. I work as director of engineering at Rudderstack. Rudderstack is an open source data pipeline company. So yeah, and with me we have Lokesh. Lokesh.
Yeah, hi, I am Lokesh, and I lead the infra team at Rudderstack, and I'll present part of the presentation.
Cool. Yeah. So let me, before we even go, like what kind of stories we have, let me first start with like what kind of setup we have at Rudderstack, because understanding that is going to be important, and it is also fun to know like how we are using Kubernetes at Rudderstack. So first of all, like what is Rudderstack? Why there is a need of such a tool? So one of the things we all know that consumer data is continuously growing. Like we have like data is distributed like across. There is like SaaS sprawl, so that way like we have data at a lot of different places, and it is really hard to collect that data. So what we are doing is we are building an open source solution, uh, where we don't persist any data. Like we simply process the data from take the data from input and then like send it to defined destinations. And we are like processed more than I would say 35 billion is a very conservative estimate. It's more than 50 billion events, because like a lot of our customers are open source, so that way I would like we wouldn't even know like how much data is being sent. I am sure like it will be more than 100 billion. So Rudderstack sits in between, like there are like a lot of sources and a lot of destination, and in between there is somewhere Rudderstack, which is processing all the data from like all the sources and sending them to the defined destination. And we are completely Kubernetes native, so all our deployments, everything is on Kubernetes only. So let's go deep into what Rudderstack is like. How does Rudderstack architecture look like? Because that will give us a better understanding of why we feel Kubernetes is a native tool to be used for Rudderstack. So in Rudderstack, we have divided the complete system into two parts. One is control plane and another is data plane. That is more similar to how Kubernetes architecture looks like today. So control plane is more like the place where we are storing all the configuration, all the observability, uh, like everything whatever is needed to get the complete visibility on how data pipeline is working. But the core aspect, like same as Kubernetes, the core things in Kubernetes also run on the data plane on different worker node. Similarly here we have data plane which process all the events flowing through it, and we are using Postgres as our storage. We have optimized it for like our specific use case. So whenever an event comes from a different source, we store it on Postgres database, and then like we do a lot of processing. And once all the processing is done, we send it to desired destination. And in our case, destination can be any SaaS service, or it can be any given warehouse. So now let's go deep into like how does our Kubernetes architecture looks like, because understanding that will be like very much important to understand like how we have built everything. So our architecture is we have built everything using Terraform. We are very much of the belief that infrastructure as code is here to stay, and that is the core like premise, that everything should be code. Like JIT should be source of truth of all infrastructure. So what we have a layered architecture, where what we are doing is initially we are creating all the infrastructure, and then we are using Helm a lot, and with the help of Argo City we are doing all our deployments. So what we have is like we have VPC networking layer created through Terraform, and then EKS that is also created through Terraform. We are using application set that comes with Argo CD, and what it does, it helps us create a base layer. So once networking and EKS cluster is created, all the clusters register itself to Argo CD application set, and in that, like Argo CD automatically deploys all the needed initial application on our Kubernetes cluster. So layer is like initially there is a networking layer, then there is a EKS layer, then there is a Terraform like Helm chart layer, which is deployed through Argo CD application set, and these three layers combined make our base cluster. So in complete Rudderstack, if anyone has to create any cluster, this is the base layer which everyone has to create. And like we are also using Argo CD with Argo CD. So Argo CD is managing itself. So that way everything is in the code. Argo CD is more like comes as GitOps model. So that way like everything is in Git. Like Basically, we push code there and it immediately get reflected into Kubernetes. So now once the base layer is ready, now we have to deploy our own applications. We are also using operator to deploy the complex data plane, because you already saw we need to, there are like different parts of data plane. So everything is deployed through operator, and plus there are like some meta services which are written by us, and then there is a control plane, and everything is deployed through Argo CD. So if anyone has to like deploy anything, anyone has to do any change, they don't need to go to cluster. They can just go to create a PR, and then someone will approve it. Once it is merged, everything will get deployed to the cluster. So in Argo CD, it supports both manual as well as automatic deployments. We are not using automatical everywhere, but still we have like at a lot of critical places, it is automatic deployment. So once you merge anything into Git, like everything get deployed. So now we have divided our services into different categories. So one of the initial categories like external dependency. In our case, because we are very much on AWS, we are using EKS for Kubernetes. The main reason is we don't want to manage our own control plane. So in that case, what we are doing is we are using external DNS controller, which basically interact with Route 53. And whenever we need to create a new application, we need to create a Route 53 entry, and that is completely managed by external DNS. But external DNS also works with different service provider. Second one is ingress. So we need to create an load balancer. And in our case, we are using ALB load balancer because it helps us create multiple rules in the single ALB. So that helps us save cost. We are also using NLB with Nginx ingress controller, but currently in our production, it's majorly ALB, and ALB ingress controller and take care of all the in traffic rule or ingress creation management. And we are also using groups in which we group multiple rules to a single ALB. And third, one of the most interesting one is AWS EBS CSI driver. So previously we were using default driver, which was coming by default with the EBS, but we started seeing some issues where the volume is not getting detached properly and stateful set gets stuck. And yes, like we are using stateful sets at a lot of different places. So that's why we migrated to AWS EBS CSI driver, which basically helped reduce a lot of such issues. So once all the external dependencies are deployed, next thing is we need to auto scale our cluster. We don't want to do anything manually. So that's why we are using cluster autoscaler, which depending on the requirement, like if the CPU is not enough or memory is not enough, what CPU cluster autoscaler does, it automatically interact with AWS and it creates more worker nodes. And we are also using cluster over provisioner. What it does, it creates some dummy pods which take provided resources. So that way we always have some extra resource being utilized in our EC2 worker nodes. And whenever we actually want to deploy any pod which is needed by any customer or like our own requirement, we don't need to directly go to cluster autoscaler and ask for a new node. We have some extra space. These pods created by cluster over provisioner are of very low priority. So anything we deploy, these pods go down first, and then they request cluster autoscaler that we need more space because the space which I had was already taken by different pods. So that is how where we are using cluster over provisioner. So with this, like our base image is ready. So that is like the core base image which we are using. Now next, because we need to deploy our data plane, for that we have created our own Rudderstack operator. So operator is basically extension of Kubernetes APIs, and anyone can write their own operator. And so this also helped us make our complete deployment very easy, because previously we had to deploy like 4 and 5 different services, and that was needed to make complete data plane run smoothly. And with the help of operator, what we did is we created one CRD which basically deploy everything for us. But it's not just deployment, it also helps us scale up and scale down our system in real time. And another interesting question is, why do we need to write an operator? We can simply run commands by increasing the number of replica. So in our case, we provide like ordering guarantee. And in case of ordering guarantee, just increasing number of nodes will not, like number of pods will not solve our problem. We need to create a new deployment and migrate everything to the new deployment. And like that can only happen when old, like everything gets flushed in the old deployment. So we have a concept of going into degraded mode where we don't process anything but we consume. So that is where a Rudderstack operator becomes a key player in our infrastructure. Other than that, we are using our own application services, like the micro ControlPlane in itself is a big microservice, like following microservice architecture. So all that thing is deployed through Helm and through Argo CD. So for monitoring, we are like now, like previously we used Tick Stack. So in Tick, like it was basically based on Influx DB. We are not using Chronograph for that. We are using Grafana for all our dashboarding. But now we are very much migrating to Prometheus. We are even using Thanos for storing data for longer duration, and also like multi-cluster kind of setup. Thanos helps a lot. And Argo CD, like as I already told, is basically that is like key component which help us deploy everything in our cluster. So like I hope this must have given you a brief idea of how our architecture looks like, and that will like help you understand more. So what happens in our case is we make a request. So whenever a new customer comes, they make a request, and as you everyone know, Kubernetes is very much API driven. So a request comes from Kubernetes deployment, through the API, it goes to our operator, and from there we create all the needed pods. So that's how, like whenever a new customer onboard, we create a dedicated environment for them. This is more of a pictorial representation of how our architecture looks like. So whenever there are multiple clusters running on a cluster, we are using AWS Route 53, ALB ingress for routing all the traffic from external world to our network. We have both shared resources, more like shared services, which we are using across customers. But then we also have dedicated services running for each and every customer. Now these dedicated services are running their own pods, or like in a lot of enterprise cases, we are also running dedicated databases inside like a namespace, which is dedicated to a customer. So that way, like all the data which is coming for the customer is dedicated, it stays in the customer. No one else can see that data. So like I hope this complete thing has given you a good understanding of how our architecture looks like. And yeah, I think now Lokesh will take it from here to talk about.
War stories are basically any large scale outages or incidents that we had, and when we had to quickly come up with some solution to make everything, bring everything up back and running. So we look at like two such examples. So, and in each case, we look at what was our setup that allowed something like this to happen, and what are all the components involved, and what exactly happened, and how we figured out what happened, and what we did while debugging that. And once we debugged, obviously we'll do like an RCA, and we come up with action items, and so we'll discuss those things as well, and how those action items helped us in the long term to prevent more such incidents. So first we'll look at the first war story is like when our entire Kubernetes cluster went down. As Mitesh mentioned earlier, we use AWS CKS for all our clusters, and we use OADC for our access management. And one of the key components there is something called aws-auth config map that contains all the information about all the users that have access to the cluster, and it also contains details like it also defines the permissions that all the worker nodes needs to access the Kubernetes API. So the idea here is to basically use AWS's IAM roles and so on as the authentication for accessing Kubernetes cluster for user. So there are other ways to do this, but the reason for choosing this is this comes by default with AWS CKS, and it also makes sense to keep the authentication in a single spot between AWS and Kubernetes instead of having two different ways of doing authentication, in case we want to revoke access or like change the type of access of some specific user. So that was the reason for going with AWS. And What happened was, like, when we started out, we had a relatively smaller team, and we had a single role call. Actually, we had two roles. One was like admin role, and another was read-only role. And everyone in the company was using these two same roles to access everything in the cluster. But as we scale up, it becomes important to have like more fine-grained control over who can access what, like what namespaces each user has access to, things like that. So we wanted to change our uh, structure of authentication, and this required a lot of changes that we need to make in the AWS auth config map, and adding more cluster roles and role bindings and so on. So we were trying this thing out on our dev cluster, obviously, and we got everything working. But then we thought, like, we should not uh, manually apply these changes on production. We should do it through Terraform. So we were again testing these things out, and during this testing, like I mean, we had like two clusters, right? We had a dev cluster and we had a production cluster. We were testing this on dev, and in between, we had to switch to production cluster to do some other tasks, and then we came back to testing it, and we forgot to switch it back to the dev cluster. So what happened was, like, we were overwriting the AWS config map, and we overwrote the production one with the dev one. So, like, they are both in different AWS accounts. So, like, what that basically means is, uh, the whole authentication system in production cluster is broken, right? So no user can actually access the Kubernetes API, and that's a smaller part of the problem. The bigger part of the problem is, since the worker nodes also use the same authentication system, like, none of the nodes were able to communicate with the Kubernetes ControlPlane API. So that meant that, according to Kubernetes, all the nodes are disconnected. So because all the nodes were disconnected, all the parts were descheduled. So they all went into pending state. And one other bad part about it is, like, we didn't even know what was happening because we didn't have access to look at what was happening. So basically, how we got about it is, like, we have like multiple levels of alerting set up on our applications, and we came to know that something went wrong because of this. And like, I remember we didn't even connect it to the AWS or config map change until some time, because one developer was working on that, and like, a lot of other people were on the call, but it took some time to realize that it had something to do with the AWS or config map change. So once we realized that that was the reason, uh, what we tried was, like, there is this concept of ownership in AWS EKS clusters. So the person who created the cluster, he'll have like extra privileges over the cluster. So even if all these accesses get lost, they can still access the cluster. So we realized that, and we brought the owner of the cluster into the call, and like, they were able to access things and see exactly what happened. We saw that the dev account was in the production config map. So luckily, we had like backups of AWS auth config maps from earlier, which we used to take. So we used one of those backups and applied it. And yeah, like, pretty quickly after applying it, like, all the nodes started connecting to the cluster, and all the pods started coming up, and everything went back to normal. So I think this whole thing took around like half an hour to 45 minutes. Yeah, or maybe even more. So obviously it's like a very bad state of affairs. So, like, this required lot of action items on our side to plan for such things in future, and to avoid repeating something similar from happening. So yeah, like, one very obvious thing that we had to do was, like, we had an on-call process of one person being on call, and they look at the uh, they take care of alerts, right? They look at the alerts for a while, and there was not a fixed process of when they should call multiple people and how it should be escalated. It was mostly a judgment call on whoever was on call. So we changed that process to make sure that whenever it's a critical alert, and like, there are multiple alerts, like, we make sure to escalate it to multiple people, and we have a way of calling a lot of high level people into the call at once. So we started doing that. And another major thing was this was all happening because our testing was manual, and our flow wasn't like very what do you say doing it on day one then on production properly. So to fix that, we wanted to do even the development and like testing parts also through Terraform, but we did not want to do them on the developer's machine, because that was the main problem, right? So they were doing something and they context switched to something else, and they missed that part. Like something similar cannot happen if you do it through a GitHub CD type of a thing. So we started exploring Atlantis for that. And Atlantis was like very helpful in that regard. So we quickly moved over everything to Atlantis. So from then on, like any Terraform change or any infrastructure change that goes to our production, it has to go through Atlantis. And even development also, it has to go through Atlantis. Like no developer can run Terraform apply from their local machines. That was the main point there. And another thing that's very specific is like AWS auth config map got overridden, and then it was deleted and so on. So we set some OPA gatekeeper rules to make sure like the config map is never deleted. And yeah, and also like we did not have a proper disaster recovery strategy then. It was more of like we strategized during the call and did something, but yeah, we realized we needed to have a plan if something else goes wrong and we don't like. The lucky thing was we were able to figure out that the config map got messed up there, but if that did not happen, it would have taken much longer for us to bring it back up. So the disaster recovery part of it is to have uh, a separate cluster running, and all the helper pods and services type of pods running on the cluster already. And whenever we want to we notice that some customer or some cluster is down, it should be easy to move them from that cluster to the new cluster. So that was part of the disaster recovery strategy. And we also wanted to have uh, all the developers be ready for any such incidents that can happen. So we started doing weekly infra drills where we like simulate a scenario, and everyone on the call, everyone in the infrastructure team tries to solve it. And like if they notice something that's wrong with our runbooks, or there is something that can be improved, we do that improvements on the call. And like this has helped us a lot, like incrementally by doing it week in week out. So this was the first story. Second story is like compared to the first one, slightly minor, but again this involved Kubernetes. One of the worker went down. So like as Mitesh mentioned earlier, like we have separate deployments for our enterprise customers. So usually when a cluster goes down, it means like most of our customers go down, like who are on the cluster. But even when a node goes down, it can mean like at least like 4 or 5 different customers going down. So this is also pretty serious problem for us. So here the context is basically EKS internally uses EC2 instances as the worker nodes. So in EKS, the control plane is completely managed by AWS. We don't have to do anything. But EC2 instances act as the actual worker nodes. And obviously all the parts run on those worker nodes. And because it's EC2 instances, there is like, it's not very often, but the instance can go down sometimes. What that means is like sometimes it can be that the instance gets terminated, but it can also mean that there is a network failure on that particular node, or like there can be cases where like some of the EC2 instances in one region are like completely down and stuff like that. So there is also another scenario where like AWS does some periodic maintenance when it wants to upgrade some things or change some configuration. So they notify us in advance, and like they restart the instances, or like they completely kill the instances at a given time. They tell us earlier to take care of it, but if you miss it, like this can also be a problem. So yeah, in this case, what happened was basically the Cube API server, it wasn't able to get the heartbeat for one of the worker nodes. So like when we looked at the logs and all our metrics and network usage and so on, like what we noticed was there was nothing coming out from that node. The actual EC2 instance was running till that time, but it looked like basically the network got disconnected on that node, right? So it went completely dark. There was nothing from there. So when this happens, like it waits for like a couple of minutes, the controller manager, and then it marks the node in not ready state. And so again, there is again some timeout after the node is marked not ready till the pod gets marked as not ready. So like the pod will get ready colon false as the status. And until this point, from the outside, we don't see any like it's very hard to notice that things are in a bad state. But like basically since the network is down, like traffic is actually not reaching the pods. But like after the ready equal to false status, like Kubernetes actively stops routing traffic to those pods. So if you have like a service that's connected to 3 pods and one of the pods goes to a ready false state, like that's a good thing basically, because like traffic is routed to other 2 pods and there isn't any downtime. So this happens, and then after this like the pod doesn't get deleted as soon as it goes to the not ready states. So there is a concept of toleration for the pods, like where you can specify how much time the pod has to wait on a unready or not reachable node before it gets deleted. So that is by default 5 minutes. We never considered to change it before, but like because of this, like the pod was still running on 5 minutes. And like after 5 minutes, like the stateless pods that get deleted completely, and then they move to a new node. Like it's more complicated for stateful pods because there is a volume attached. So what happens is like the pod gets deleted. So it's like when you run pod delete, right? Like sometimes it doesn't get deleted often if there is some finalizer that's blocking it. So here the finalizer is that the node is the volume is not detached. So it took some time to detach that pod as well. And so like how we responded to this event was like because of some of our like ingestion services going down, we got alerted right away for this. But the first time it happened, like we didn't know exactly what happened. Like we found out that some parts were in like terminating state or deleting state or whatever, but like it took us some time to figure out that it was because of a node going down. By the time we figured out and like we did some research on what to do in such scenarios, like all of the previous things happened, and everything moved back to a new node and like things started coming up. So we didn't have to do anything. But after this happened a couple of times, we did a lot of research, and like we added alerts on when a node goes into not ready state or unreachable state. So we realized like much sooner what exactly is happening. And as I was saying, there is a concept of toleration. So we change the tolerations of critical pods that needs to be running all the time to 20 seconds. So like whenever a node is not reachable for 20 seconds, the pod gets deleted from there and moves to a new node. And we also wrote like runbooks and scripts for deleting all the pods on a single node, and also delete all the volume attachments from that node. So this helps us in like bringing the pods like stateful pods up quicker. So like this happened multiple times after that, and like we were more ready, and things weren't down for longer after we took the we wrote the scripts and so on. And coming to like RC of the things and action items that we took here. So again, like here also this meant that one on-call person might not be very reliable in such scenarios where like multiple customers are affected. So we started routing the alerts to multiple people when it's like so as I was saying, like we have alerts for each customer being down. So when there are multiple customers down, like it means something went wrong on the infra level. So we started routing it to multiple people, and then we change the node timeout setting where like we delete the node much earlier when the node is not reachable, because we observed that once the node goes into once the heartbeat stops coming, usually doesn't come back up all that often. So like one safe option is to like kill it much quicker. And we also try to change the max wait for unbound duration. This should help in the detachment of volumes and so on. But uh, this felt when we tried doing this, it felt a little complicated, and we faced some blockers there, so we didn't do that. But we have some workaround for this part. And I think the most important part here is we started running all the important parts in HMO. So excuse me. So even if one node goes down, the application is still healthy. So we have like an reverse proxy that routes all the requests, that takes all the requests and routes it to the relevant service. So initially we used to have one per customer. Now we have two per customer with smaller resources, so that like we're not bringing up the costs all that much, and we run them on different nodes. So even if one node goes down, the application is still healthy. And as I was saying, AWS also does this maintenance type of a thing where they notify us in advance, but it's a notification on AWS console. So if you're not paying attention, like it's very easy to miss, and we missed this multiple times. And like we recently figured out that we usually get notified of this earlier. So we use like Event Bridge and SNS, and we listen to that topic, and we listen to that event, and send us reminders on Slack, so so that we are ready to take care of these things. So yeah, thanks for your time, and